In this video, we want to emphasize quicksort. It's another algorithm used to solve the sorting problem. Last time, we checked for merge sort and discussed divide and conquer technique, and we emphasized decrease by constant factor, decrease and conquer technique, and we draw the recursion tree and we check the time efficiency. In this video, we want to check a quicksort. It is also a usage of divide and conquer technique, but it is based on variable size decrease and conquer. And in this video, we want to check what is this algorithm could be, and how to choose pivot, and what is the time efficiency, and for different cases, what could be the specific time efficiency. And we will go to the details. First, compared to the merge sort. The merge sort, we divided the sequence given the array into two parts, half and the right, the left and right, and the left half and the right half, and we conquer each half, and then we combine the results. In that case, we see that the results, value results get for each level came from the combined side. And in this quicksort, the author proposed this method in the 1962, and the idea here it is they want to say, okay, in each division we already decide, well, it is one of the elements should be stay, right? One of the elements should stay in a specific position, and use this one cut the whole sequence into the left part and right part. So this is quickly place the elements in the correct position. So with the details, let's take a look at the methodology. And the quicksort, we partition the array into two sub-arrays such that elements in the left part, smaller the elements in the right part. So the whole sequence cuts into two parts. And based on the specific elements you choose, we choose a pivot, but finally we use this pivot to split the whole sequence into two parts. Always the left part smaller than what you have the right part. So the used pivot will stay here as x, right? As x. X will be stay here, right? All this one smaller than what you have the pivot, and all the right part larger than what you have pivot. And then in that case, we place the x is pivot in the correct position, the q is correct position for x. We recursively sort two sub-arrays, the left ranging or the right part, and then in that case, we really don't need to combine the results from each part, because every time we are sure that one of the elements should stay in the correct position separate to half. We don't need to adjust the position for element x. We don't need to adjust the location of this pivot. And they have two partition algorithms, and both are linear. The linear ON, big ON, the theta n partition algorithm. So we have two algorithms, Horn's algorithm, and which partition around the first element of subarray. So choose the first element in the beginning as the pivot, and use this one as the x, and separate the whole region into the left part and right part. Now Milton's algorithm is different. The partition around the last element is okay. Let's use the last element as the pivot, and choose this one as the pivot, and separate the whole sequence into two parts. Although the algorithm they use different, the element in a different location as the pivot, but the idea is the same, and use this pivot to separate two regions. And the x will be in each iteration, x will be placed in the correct location. First, let's take a look Horn's partition algorithm, and we will emphasize this algorithm. In this algorithm, we ask different questions. First question, First question, can we change this statement? Can we start from P? Can we initialize I to be P? Can we initialize J to be R? Why we need to initialize I in the beginning, in the location before the P? Why we have I to be here and the J is supposed to be here? Right? This is one question. Second question, can we switch these two statements? This is the first question. This is the second question. Can we switch them? The third question, if all the value or elements are same, if all the elements are same, what could be this procedure, right? If that is the case, how to analyze that? The first question, if sequence is in order, what to do? Fifth question, that it is a reversed order, and what could be the solution? Okay, let's take a look. In high level, we use this home partition to retrieve correct location of this X. And then we use the same procedure to quickly sort the subsequence from P through Q. And we use the same procedure, quick sort, to sort the subsequence from Q plus 1 to R, right? So in that case, we can imagine that every time you place this in the correct position, you follow the same way. Some elements should be correct position, same way. So when there is the recursive down, in that case, every element is supposed to stay in the correct position. Use this way to solve the problem. Now let's take a look. In the Holmes partition algorithm, we select a pivot element, and we initialize pivot to be in the beginning, the element in the beginning of the array, and we grow the two regions from P to I, from the left to the right, and we grow another region from J to R, and is from right to the left. It's corresponding to, if this is the whole sequence, and we use this one as the P, this one is the R, and the pivot is here. We wanted to grow this region. In the beginning, we have only nothing is here, right? We want to check how many elements should be smaller than X, and how many elements which is larger than X. So we grow this region, we grow two regions from the left to the right, and from the right to the left. And I will always change based on what we move, this pointer, right? We grow this region with the I increased value. We grow this region when the J increase. We grow this region when I plus, right? And such that every element in P through I will smaller than pivot X. And in this part, J through R, and this one always larger than or equal to X, right? We use pivot, we treat it as X. So this is the idea. The two regions API and AJR grow until AI greater than pivot and larger than or equal to AJ. Assume these inequalities are strict. AI is too large to belong to the left region. AJ is too small to belong to the right region. In that case, we exchange AI with a j for future growing in the next iteration. This exactly same as what we discussed for this code. And with initialize I in the before the P and J after the R, and in this loop and in each iteration we grow this region from P through I, and here what we have these elements in the i's position cannot belong to the left part, right? We stop here in each iteration for I, and also for J we grow from the right to right, from the right to left, and here these elements at the J cannot belong to the right region. Then we we swap the elements in these two positions. We continue this procedure until I and J meet, or I it is larger than J, right? Because if it's smaller than J, we exchange. Only when they are equal to J, it means we scan every element, or I larger than J, right? It means we crossed the middle line. Cross the splitter. It's hard to say middle line, but we cross the splitter. Okay, so it's important AP is to understand this Horn's partition algorithm, and this is very important to understand. AP is chosen as the pivot element, and AR is selected as pivot. AP is chosen as the pivot. If AR is selected as pivot, it may yield a trivially splitter A equal to J equal to R. Occurs when AP through R minus I smaller than pivot. Then the quicksort may loop forever since the Q equal to R. It means in this solution, if we happen to choose the last element as the pivot, then we have to adjust the code because it will cause that loop. Take a look at this example. Let's say we have 8 elements, 8 numbers, and P is in the first location, R is in the last location, I is equal to P minus 1, and J starting from R plus 1. And in that case, it is in the loop, we will check starting from J first, and it check for P, right? And for R, it means at J's position, you got element 7, and then in that case, 7 is larger than the pivot 5. Then in that case, this is in the good region, and then increase J and check 3. Since 3 is smaller than R, 3 cannot be held in the right this region because this odd part should be larger than or equal to pivot, right? Let's use X to simplify that. And so they will pause here, and then they will quit from the repeat loop. Then go to the left side, and increase I, go to equal to 5, and it will stop here because it's equal to X pivot. And in that case, 3 has to be placed in the left region, and 5 could be placed in the right region because it should be larger than or equal to 5. Swap 5 and 3, we have these results in the first iteration, right? In that case, we exchange 2 elements. We finished 1 iteration, and in that case, we increase what we have the left region from long through 1 element, and the right region we increase into 2 elements, and all of this right region greater than or equal to X, and the left region which is smaller than or equal to X. And go to the next iteration, and still starting from the right side, and in J decrease, you got elements 1, and 1 cannot stay in the right region, and it quit from the repeat loop, and increase I, you got 3, and this is okay in the left region, 2 is okay. Then go to the 6, and 6 cannot belong to the left region anymore, and then in that case we have to swap this element at the index I and index j, right? Because they cannot belong to the left region, cannot belong to the right region, and that's good to swap them. And after swap them, this is what we have, and this is the second iteration. Once you go to the second iteration, and it's okay because it doesn't finish, I still smaller than j, right? We see the stop in for the outer loop only when I equal to j or I is larger than j. So we go to the iteration 3. Let's see I3, right? So in that case, it is j decrease, go to 4, and repeat, quit from the repeat loop, and I increase. And since 4 is okay in the left region, I increase 1. So I go to the next one. And then of course, it end into the right region, which is suppose is larger than or equal to x. This left region is blue region is smaller than equal to x. So in that case, they have to quit from the repeat loop. In the second repeat loop, I had to be stopped here, and in that case check and I is larger than j. In that case, you finish the partition. When you finish partition, you return q. The q is written. In that case, return q, and then the next step it is we say in this case. We know the elements at the Q's position, they should be stay here, right? Because it's correct position. And later, we just need to use the same procedure, check the blue region and check for the red region. Okay. And this is just as what we discussed. Let's take a look at the correct list of Horn's algorithm. Based on our discussion, it seems good, but we have to prove that. And they have different things we want to check. First, we make sure the indexes x and j level reference A outside the interval AP through R. Split is always non-trivial, and at the termination, j should not equal to R. If j equal to R, in that case, in what happened? If j equal to R, in that case, it means the element at the R's position should be equal to pivot, or that it is smaller than pivot, right? It's only case. And then in that case, if you, in the final termination, allowed to do that, and then in the case, the I have to be increased to the last element. We see this is not possible. The reason it is what we have the I starting from p minus 1. And definitely they will work for the one iteration to get the p's position. And if they choose this one, I will be increased to be I p plus 1. So it is suppose it need to have at least 2 loops. If the elements in the R's position is equal to pivot, in that case, they will swap allowed R decrease, allowed this j equal to the R minus 1. If they happen, this number is smaller than the pivot, also allowed to go to the next iteration. So the second node in the constraint, which corresponding to how many iterations need to happen. And for us, we say the outer loop should at least be executed for once. So it means the j will not equal to R because you go to the next iteration, right? That is no constraint. And the second contain index level reference A outside the interval A, P through R. So we already proved that it's the same as what we discussed for B. Every element in A, P through J smaller than every element in A, J plus 1 through R, a determination. This is also what we want to check. To check for this question, and let's use specific notation. K corresponding to number of times while loop iteration until termination. This is the final iteration. And we use IL and JL corresponding to values of IJ indexes at the end of iteration. L corresponding to number of iterations, IL and IJL corresponding to location of I and J, the pointers, right? Pointers of I and J in the L's iteration. And we see we always have I1 equal to P and P smaller than J1 less than or equal to R. This corresponding to in the end of the first loop. Definitely we have the I pointer at the P's position and P position, right? And also the J, the end of the first loop, J should suppose equal to R or between P and R. Okay, we see that at the termination, we see that only have two possibilities. Ik equal to jk, it means the last iteration I and j meet, right? This is one of the case. And the question for you it is, when is I and j become the meet? They meet at the same location when it happen. We only have one case. It is the value, the element at Ik and jk position is which equal to just happen to be pivot. In this sort, it allow have a duplicate elements. The second case, it could happen in the final iteration, and which corresponding to Ik equal to jk plus 1. And it means what we mentioned before, right? Ik, I larger than k, I larger than j, or I equal to j, the whole loop, outer loop, finish. So we check when k equal to 1, it corresponding to the last loop, the only have happened for one big out loop. And k equal to 1 occurs when AP plus 1 through R, which all of them larger than pivot. So all the value after the first element is greater than P. We do not need all the elements stay in exactly, strictly ascending order. We don't need to. We just need to have all the elements. If that is greater than pivot, in that case, the only have one outer loop. Then you decide what could be the position for this pivot. And also in this case, although they only have one outer loop, but it still needs to scan each element, right? Because the J have to move from R plus 1 position to P's position. So in this case, partition also need to have big O(n) runtime. Partition still have big O(n) runtime, and in this case, you will find out this partition is totally unbalanced. So in this case, it's not efficient because of the whole algorithm lead n to the power, the n square runtime. When k larger than 1, we check for different cases to prove this algorithm is correct or not correct, right? First, we check if k is equal to 1, and in that case, we see the only happen it is all the elements after the first statement, after elements the elements after the first location should be greater than pivot. Okay, when k larger than 1, in that case it is in the last loop, I and j, they stay not in the first location, and with I key, let's assume I key minus 1 smaller than J key minus 1, right? This makes sense. The reason it is only when the I key minus 1 smaller than J key minus 1, you can go to the next loop. So this is fine. So based on this what we mentioned, I key minus 1 smaller than J key minus 1, we have different case to check for last loop, last iteration. So the last iteration, when it finishes the whole out loop, we have J key. J key should be between I key minus 1 and J key minus 1. If it happen I J key equal to pivot, in that case I key happen to equal to J key. It means I move from left and J move from the right. They happen to meet in the middle, in some place in the middle, right? In this green region. And this case 1. Case 2 happen, it is IK equal to JK plus 1. It's just across this some place in the JK and move forward for one more place. Or what it happened? It happened, we see it in this outer loop. We have 2 repeats. We start from the right side. We increase this right region, right? This right region, and when the J key increase to specific location, it cannot move anymore. It corresponds to define the elements in this J key position smaller than X, and it suppose it belong to the right region. So it stop at this position, and then so we check the second for repeat. I increase the value from the blue region and increase that until when the mid J key still not stop because it belong to right region. And when you check the next one, and since all the remaining after this J key, all these elements of the J key position, which is already proved to be larger than X, so definitely I key will stop after J key, right? One position after J key. So it means in the end of this iteration, the last iteration, the I key will, the difference between I key and the J key will never more than 1. Okay. And so this is the I key and the J key. They stayed in the middle of in some place of this green region. And another case corresponding to when J key decrease and the whole right region increase, and it meet to the end of the blue region, right? In that case also the I key is equal to J key plus 1. So you use this way, we can prove the whole and the partition algorithm is correct. And also we can check the runtime for this partition algorithm. It is ON. It scan the whole sequence to decide this pivot should be stay. Also use this pivot, this location, to split the 2 parts. So the total runtime for partition is ON. Okay, so this is another methods algorithm, and if you have time, you can take a look. We have the slides posted online. I think that is all. Yeah, exactly, that's all. Okay, I stop here.